Hello students, in this video I'm going to tell you a little bit about set theory at an informal level, a very informal level, kind of the level you would need if you're going to be doing some things with sets but not really delving deeply into set theory itself. And of course I left my good camera at the office, and so this camera makes me look even scarier than I would look otherwise, but hopefully the stuff I write on the board will be legible, and that's kind of what really matters in this context. So a set is a mathematical way of talking about a family or a collection of things that we call elements. So a set is made up of elements. And the simplest way to understand this is by looking at some examples. And the first example I have here, notice the notation. I open a brace, and then I put 1, 2, 3, and then I close off the brace. Now this means a set, so this whole thing here is a set. And then the 1 and the 2 and the 3, these are elements. Elements of the set. So this is a common way to represent a set. You open a brace and then you put a list of things in there, and the list of things, each of those things in there are the elements. And there's many other examples of similar things, like I could start listing some letters, A, B, C, D. I guess I did something like that over there. Let's put a few more. E, F. So here I have a set with 6 letters in it. These are the elements of that set. Now, that's a very reasonable way to describe a set if the set just has a small, finite number of elements in it. Just list them all. That gives you the most information. But in many cases, we're interested in sets which are large, very large, and they're too large to list all of the elements. In particular, they might be infinite. Now, that's not as scary as it sounds. It's something you're very used to, because infinite in this context usually just means that they go on without stopping. And that's what happens when you're counting. You start at 0, 1, 2, 3, 4, 5. Well, it doesn't stop, does it? You can go on as far as you like. So if I try to represent that sort of collection or family by just listing the elements, well, I have to decide how many am I going to list. So I might open up a brace and then I start 0, 1, 2, 3, 4. Well, what then? Well, 5, 6, 7. But there's a limit to how much ink I have in my marker. So I'm going to write a dot, 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 and then I'm going to close off the brace. Now what the dot, dot, dot means, and this is a very general thing, you may be familiar with it already, you probably are, I imagine. The dot, dot, dot always means and so on. So it means keep on going the same way you have up to this point. Now for the and so on to be clear, to have a clear meaning, you have to have listed enough things before to have established a pattern which is recognizable. And in this case, of course, I have 0, 1, 2, 3, 4. It's obvious the next thing should be 5, and then 6, and then 7, and so on. Which is why I can say and so on in this case. So this is okay. This is an okay way to represent a set, and it's clear what set that is. It's clear that it includes all of the numbers that you would count with. But it's also nice to be able to have a briefer, shorter way of describing this, and so we do. We assign a special symbol to this, and that's this symbol, N, over here. And you see I wrote it over here, N. Now why do we use N? Well, the N stands for natural numbers. Now, something that I've encountered before in talking to people is that some people were taught, going back to junior high or maybe even before then, that the natural numbers should start at 1 and that 0 isn't included in the natural numbers. And so what they've been taught is that if we want to include 0, we should say whole numbers instead. So that's an alternative definition that you sometimes see. But mathematicians don't do that. They don't call this thing the whole numbers, they call it the natural numbers, and they use this symbol for it. And a good reason why is because this number 0, which is included here, we want to include 0. So we want 0, and why do we want 0? Well, because 0 has a special property. It's the additive identity. And there might be a glare up here, so let me say it again. Additive identity. And so what that means is that if you add 0 to anything, you get that same thing back again. And it's nice to have a number like that in your number system, so we choose to include it in the natural numbers. So whenever we say natural numbers, we're going to mean this thing starting at 0. And it's nice to have a symbol for it like this instead of have to write that out every time. So what's this third example over here I wrote, that z there? Well, this is another thing you're familiar with, and that's the integers. So this is another familiar set, integers. And we write this as z. And what are the integers? Well, to write the integers, to represent the integers using these braces and so on, I could do this. I could open a brace and then I could write a dot, 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 comma. Why would I write that? Well, you'll see in a second. Then I could write -2, comma, -1, comma, 0, comma, and let's see if I have enough room. 1, comma, 2, comma, dot, 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 and then I'm going to close the brace. Now, notice I have a dot, dot, dot over on this side, and I have a dot, dot, dot over on this side. And that means that there are two and so on type statements here. So this would say and so on going this way. And this would say and so on over here. Going that way. And so the meaning of that's relatively clear, I hope. If you started at 0 here, and then you count 1, 2, well then by then the pattern is clear. Next you would go 3, 4, 5, 6, and so on, going that way. And then similarly, if you started at 0 here, you could go the opposite way. You could go to -1, -2 on the number line. And then by then the pattern is clear. You go -3, -4, and so on, going that way. So it's clear enough if I write this what I mean. But once again, it's nice to have a single symbol for it. Now, you notice the way I'm writing these letters here, the N and the Z, it's like a font almost. It's like a special font. And so there's actually a name for this. It's called Blackboard Bold font. And it's used for number systems. Number systems. And so a lot of the more familiar sets that we're used to dealing with all the time already are these number systems. Particular collections or families of numbers. And so we use this type of font. So why is it called Blackboard Bold? Well, if you were going to write something bold, then you would kind of, make the lines thicker, right? So I might write the N, maybe I would write it like this, for example. But you see how long it took me to do that. And of course, nobody's going to do that. So what they're going to do instead is they're just going to write, double lines like that in order to show that it's doing the same thing. So it's a convenient way to write it in the context of the blackboard. So that's why it's called that. But whenever you see something written that way, it usually means a number system. So if you forgot which one it was, then at least you can narrow it down to think, well, it should be some number system, and then try to think about which one. Well, the next one we're going to talk about, the next familiar set we're going to talk about is another number system, and that is the rational numbers. And this is often written with a blackboard bold Q. Why Q? I mean, so when you see the Q, you can think quotient. Q for quotient. You know, quotient, a slightly more fancy way of saying fraction. And you know that rational numbers can be represented by fractions. In fact, that's how you're used to representing them. So this is all fractions. That's what it is. All fractions of integers. So you're thinking about things like this, a over b, where a and b are integers. But, you know, sometimes you have two fractions which involve different integers, but they end up being the same fraction. So you know, there's details in terms of actually explaining this precisely, because, well, you know, for instance, 1/2 is the same as 7 over 14. And so that's a different a and b than what that is, but yet they mean the same rational number. So it wouldn't be quite right to say that rational numbers are precisely fractions, because then you would get more than what you actually have, because sometimes the two things agree. How do you tell if they're the same? Well, you cross multiply, right? That's how you tell. So you say all fractions of integers, and then if we wanted to write out what the details are, we'd say where the fraction AB means the same thing as the fraction C over D if AD equals BC. If you get the same thing when you cross multiply, let me write a slightly nicer equal sign there. So that's, of course, one way to talk about rational numbers, and that's, so fractions, another way to say that is quotients, and that's how you remember that this Q thing is supposed to stand for rational numbers. Well, another way you're used to representing rational numbers is by decimals, right? Certain special kinds of decimals, that is, either ones that terminate or else ones that repeat after a long time. So, you know, for example, 1 over 3 is the same as 0.333, and then of course the 3's keep on going, and so you have a fraction representation, and then you also have a decimal representation. And, you know, the decimal representation is a lot closer to being unique than what the fraction representation is, because with the, you know, with 1 over 3, you could also write this as, for example, 4 over 12, and it would be the same thing. And there's only one way to write this as a decimal. Now, when I said almost unique, because it's not quite unique, why is it not quite unique? Well, 1.00000, and, you know, let the zeros go on forever. This actually means the same thing as 0.99999, and let the 9's go on forever. Those are actually the same rational number. That might bug you, I guess, but it's true. So if you don't believe me, then you can like bug me about it in class or something like that. But anyway, you can write a rational number as a fraction in a variety of ways, or as a terminating or repeating decimal. So we're very used to these, of course. And then, so we did a small finite set, we did 3 number systems. Another number system, and of course the one we're going to be talking about most, I guess, is the real numbers here. And so this is real numbers, and once again we're using this blackboard bold font to represent them. So R for real, that's pretty clear what that's supposed to mean and why. And so this includes all of the rational numbers to begin with, but it also includes more. So, and it includes irrational numbers and irrationals. And you're familiar with some irrational numbers, like square root of 2, square root of 3. I mean, I could take, if I take any prime number, for example, and take its square root, then I will get an irrational number. And you can actually prove all of those the same way, that they're irrational. I forgot a comma here. And then there are other things. So these are irrational, but they are what's called algebraic, which means that you could write some polynomial equation, and then one of these numbers will be a root of that equation. So they are algebraic. But then you have things that are not even algebraic, and the prototypical example of this is the number pi, the ratio of circumference to diameter in a circle in flat space. This is what's called a transcendental number. And so transcendental means that if I write some sort of polynomial equation with integer coefficients and I find the roots, they'll never get a number like this. It's transcendental. It transcends the algebraic realm in some sense. And another one, of course, is e, which is the base of the natural logarithm. And those are sort of our two favorite transcendental numbers. But most real numbers are transcendental. And it's funny because we know so few of them, or we, are familiar with so few of them off the top of our head, and yet they make up most of the real numbers. So we're getting a lot of examples of sets just by looking at familiar number systems. Now I wrote one other little example over here, and of course we'll see many more examples besides these, but I wrote one more example there, and that's the empty set. So this has a symbol which is like an O with a slash through it. Empty set. Now I've been writing, for these two at least, for the natural numbers and the integers, I wrote them as lists. And then I didn't write the rationals as a list. You actually can. It may not be obvious how to do it. But then you cannot write the real numbers as a list. There are too many. Many too many. What if I try to write this as a list, the empty set as a list? Well, it's empty, so it has no elements in it. So I'd open a brace and then I just close it off because there's nothing in there. So this is just saying no elements. Now, something that's a common source of confusion is that people will somehow want to equate the empty set with the number 0. So let me just say here, do not confuse the empty set with 0. These are two different types of things. So they can't possibly be equal to each other. How are they different types of things? Well, the empty set is a set. So a set, it's not just an individual thing, it's a collection of things. Whereas the 0 is an element, it's a number, it's an individual number. And so it can't be the same as a set. Now the empty set is a set that has 0 elements. That's right, because I could say no elements. That's the same way as saying 0 elements. But that doesn't mean that it's the same as 0. It just means that there's nothing inside it. It's like a box. You open a box and there's nothing inside the box. That doesn't mean there's no box. It just means that the box is empty. There's nothing inside it. Okay, so these are a few examples of sets and also some preliminary stuff about some of the notation that we're going to be using.